New pattern. Woo! Introduction to tree depth first search. So we're going to go over the pattern, its real world applications, and some problems that we can solve with it. Okay. About the pattern, yada yada yay, rough outline. Okay. So a tree is a graph that contains the following properties. It is undirected, right? And this is what undirected means: a graph with edges that do not have a specific direction assigned to them. So it's two-way, not just one way, one way in the case of a directed graph. Now it is a cyclic, so a graph without cycles, no cycles found anywhere. It is a connected graph where any two vertices are connected by exactly one path. So you can find a path from one vertex to any other vertex in the tree, and it's a single path to get there. Its nodes can contain values of any data type. The following key features set trees apart from other data structures, such as arrays or linked lists. They organize data in a hierarchical manner with a root node at the top and child nodes branching out from it. Okay, so there's hierarchy, and they are non-linear, which means that the elements in a tree are not arranged sequentially, but rather in a branching structure. All right. Now, the time complexity for search and insert operations in trees is typically O log of n, where n is the number of elements in the tree. In contrast, the time complexity for search and insertion operations in arrays and linked lists can be O of n. So linear time versus log time is better, where n is the number of elements in the array or list. There are multiple ways to traverse trees. Now, a naive approach to exploring a tree would be to revisit the already traversed nodes. More specifically, we start at the root node and traverse a particular branch all the way to the leaf node. Then we start at the root node again, why? And explore another branch. In this way, we'll revisit many nodes over and over. And that makes our time complexity, what? O of n squared, in the worst case, because we are taking a naive approach. Now, we have the CHAD tree depth first search, and it is another traversal method that explores the tree by traveling as far as possible along a branch before exploring the other branches. So it visits each node of the tree exactly once, and it guarantees a traversal in O of n time. There are three main methods to traverse a tree with the tree depth first search pattern. So three main methods: the pre-order, in-order, and post-order. And I've had such a hard time getting this to stick in my memory because I don't use it often. So it's just good to know, really. So for pre-order, we start at the root node, visit it first, then we recursively traverse the left subtree followed by the right subtree. This means we explore nodes in the order of root, left, and right. So root, left, right, pre-order. It's like starting at the top of the tree and moving down, exploring branches as we go. Here are the steps required to implement this algorithm. So I say this is the traditional way for people who read from left to right. Start from the top, left, right, top, left, right, top, left, right. So traverse the left subtree. So we recursively traverse the left subtree starting from the root node. Visit each node in the traversal. If the left child doesn't exist, we move to step 2, where we are looking at the right subtree. And then we repeat step 1, starting from the right child of the current node. And if the right child node doesn't exist, we visit the current node. We repeat steps 1 through 2 until all the nodes in the tree have been visited. And now we have this snazzy illustration. So yellow is unexplored, purple currently being traversed, green is traversed and visited. So start from green, right? We've seen the root, go to the left again, back to the top, right? We've been here before, then go to the right, back to the top, back to the roots, then to 2, then to 5, back to 2, now to 6, back, and we're done. Okay, we've gone through every single thing. We are happy, we are glad. Now, the meaning of visit depends on the application. If we're calculating the size in bytes of the directory structure on a disk, for example, this may involve accumulating the size of the files in a particular directory. Okay. Now, for in order, I'm gonna skip all this and just go straight to the diagram. So you do left, parent, right. Okay, so in this case, we go down all the way to the left, then the parent, then the right, back to this parent, then this parent. Okay, that is interesting. Okay, so left, then the parent, then the right. Okay. Super confusing. I don't know why. But left parent, then right should be 4, right? Then back to parent here for 0, right? Then right, okay. Then for the right subtree, all the way down to the leftmost leaf, back to the parents, then down here. Okay, whatever. Now the post order traversal. So start from the root. So we're doing left, right, parent. What's the difference between this and pre? Pre is left to right. Okay. That's why I just refuse to stick. It's like super weird. Okay. And so in this case, all the way to the left once again. Okay. Oh, do the children before you like come to the parents. Okay. But so do the children. So 5, 6, then 2. Okay. Okay. Before you now get to 0. So the parent is last in this case. In this case, the parent is in the middle, right? And in this case, the parent is first. Okay. All right, I guess that's some useful, something useful. So, and it goes level, is it level order? Level order for the subtrees. So 0, then 1, then 3, then 4, then 2, then 5, then 6. Okay. And in order is 3, 1, 4. So leaf, parents, leaf. Roots is in the middle. Okay. And then leaf, parent, leaf. Okay. Fairs. Why do they even call that in order? How is that in order? To me, pre-order is the real order. I mean, look at that. Anyway. And then for post, we have leaf, parent. Wait, what? Okay. Leaf parent. Okay. 3, 1, 4, 3, 4, 1. Okay. And in this case, post order, the root is the last thing you see. All right, that's interesting. Okay. So now, while these are commonly discussed in the context of binary trees, they can also be generalized to non-binary trees with any number of children per node, also known as Emery trees. In such trees, the traversal methods can still be applied by defining an order in which to visit the nodes. And now we have these examples. Path sum, determine if a tree contains a root to leaf path, such that adding all the values along the path equal the specific sum. And we'll look into some problems like very shortly. So I don't find when they give examples here as useful as just like now, does this appear somewhere in the solution set? No. So you're gonna see examples anyway, so just like stay tuned. If you're watching this video, you're probably an overachiever already, so well done. Most people don't watch these ones. And here's another example. Determine if a tree is a binary search tree. So now, how do you know if your problem matches this pattern? So first of all, you have to be given a tree. So the input data structure is in the form of a tree, or the cost of transforming it into a tree is low. Next, we have balanced to low branching. The tree is balanced or has a low branching factor, where DFS provides efficient exploration due to less recursion or backtracking. Now it's hierarchical. We deal with hierarchical structures like org charts or family trees, where traversing from parent to child nodes or vice versa is essential for problem solving. Now if the solution is near the leaves, if we believe the solution is near the leaves of the tree if the problem requires exploring all nodes at the same depth before moving to the next level, okay, that's BFS. And now if you need to traverse along paths, components of the solution are listed along paths from the root to the leaves, and finding the optimal solution requires traversal along these paths. A classic example is finding the height of a given tree. Nice. Explore all possible paths. So this requires exploring all possible paths in the tree to find a solution or enumerate all valid solutions. Instead, if finding the shortest or optimal path is crucial, especially in scenarios like route planning or maze solving, BFS might provide a more suitable approach. So real world problems. Okay, these are nice. These tend to be nice. So now when you want to find products in a price range, so we convert the prices of all products into a binary search tree and perform a variation of pre-order traversal on the tree. We start at root, check if its value lies in the range. If it does, we add it to the output array. We then check if the value is greater than or equal to the lower bound. If it is, we call pre-order traversal on the left child. Okay, so it's like binary search tree doings. All right, and then dependency resolution. Oh, when you're doing imports in your code. In the dependency graph of a software project, each module is represented as a node, and dependencies between modules are represented as directed edges. As it traverses the graph, it naturally produces a topological ordering of the nodes. In this ordering, each module appears before its dependencies, ensuring a valid build order. And then syntax tree analysis. In compilers and interpreters, source code is typically represented as syntax trees. DFS can be used to traverse these trees for tasks such as code generation, optimization, or static analysis. All right, strategy time. We're going to match problems to their pattern. Zigzag level order traversal of a binary tree. I'm going to say some other pattern. Maximum path in a binary tree. Start and end at any node in the tree. Maximum path sum. I really don't know. Could be wrong. So the lowest common parent node. Connect all siblings. I'm sure. Oh, wow, I got everything. Incredible. Okay. Explanations. 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 I'm not going to get into it. Thank you for watching. See you in the next video. Cheers. Cheers.